Hey, thank you all for your time, and greetings to future people on YouTube watching this. I'm really excited to share with you about Superstaq, which is our flagship quantum software platform, and it's designed to increase quantum performance by 10x using software as a force multiplier for the underlying hardware. Now, at last year's Q2B, we announced this platform in a closed beta, and as of September of this year, I'm really excited to share that this is in a public beta that anyone in the world can access to unlock the potential of underlying quantum hardware. And what I'd like to give today is an overview of where we are with this platform, what it does for our users, how they use it, a preview of what's coming next, and I'd actually like to start with somewhat of a live demo. So live in the sense that we ran this just a few hours ago. Thank you for the AV team for cooperating with our latest version of this. But what we did is we prepared a GIF of exactly how to use Superstaq. So if you can go ahead and click play, the first thing that you're going to see, and then you can pause it again actually immediately, is Superstaq is directly integrated into Qiskit with Qiskit Superstaq. That's what you see here, as well as Cirq with Cirq Superstaq. These are two open source front ends. And when our users come in, all they have to do is import Qiskit Superstaq as QSS. Once you've got that foundation, continuing on with this is almost the same as using Qiskit. Just as in Qiskit, you can create a provider, and from that provider, you can fetch any backend. In this case, we're going to do IBM's Brisbane QPU, which is a 127 qubit machine with IBM's latest technology. So if you go ahead and click play again, we're going to carry through. We're going to be able to do a head-to-head comparison, use IBM's Qiskit runtime service. And the benchmark I'm going to show today from a few hours ago is a GHZ circuit. And if you pause right here, this is a benchmark of quantum algorithms that is really the gold standard. It's a coin flip between getting all zeros 15 times and getting all ones 15 times with roughly 50-50 odds. So this is a fully entangling quantum circuit with a lot of CZ, CX gates, 2-qubit gates. And what we're looking for here is how well can we produce the ideal probability distribution of 50% zeros and 50% ones. What I'm going to do next is show you a little bit about the underlying technology that drives Superstaq. And so if you replay, what you'll see is we're going to take this circuit and run it through Superstaq with just a backend.compile call. That goes to our cloud server and throws all of our technology at the circuit and comes back with a compiled circuit. We're going to draw it out, and I think the best way to visualize it is if you pause here. This is the output of what Superstaq has produced. Now, I'm going to get a little bit technical for a couple minutes just to explain what we did that's very unusual. And I'll give the disclaimer that most of our users never really interact with this picture of what's going on, but it does capture the essence of the underlying technology and IP that we've developed. What you're seeing here is the actual execution of this quantum program in nanoseconds at the x-axis. And each of these rows corresponds to an individual qubit. Where there is a connection between two qubits is a 2-qubit entangling gate. I want to highlight two of the technologies that we've developed that are showcased here, especially if you zoom in. One of them is you're never going to see something like a CNOT gate or a CZ gate in Superstaq. What you're actually seeing here when you have the links between two qubits is the most fundamental device physics interaction in the hardware. In IBM's case, it's something called a cross-resonance interaction, and it's a custom pulse that we pull out from the hardware and expose to the user. The second technology that is really being exemplified here is something called dynamical decoupling. This is a way to insert extra gates into a quantum program to dramatically increase the performance of a circuit. And if you see those little cyan-colored X gates, those are very intelligently scheduled X gates that produce this dynamical decoupling sequence. So we'll keep going with the demonstration, and what you'll see is we've produced this pulse gate circuit. This is a real differentiator for Superstaq. There's no other technology out there that produces pulse gate circuits. But ultimately, we want to see how well does it run. So if you go ahead and click play, we're just going to do backend.run with Superstaq of this GHZ circuit. And then we want to compare it against Qiskit runtime. And if you pause here momentarily, I'm just going to show that for having a very fair comparison, we're putting Qiskit on its highest possible optimization level, and we're equipping Qiskit with dynamical decoupling. So if you go ahead and play, we ran this just a few hours ago. Again, Superstaq versus Qiskit runtime head-to-head, and sat in the queue for a few hours. But when we got results back, and we're going to refresh this GIF just momentarily, we're going to get back results from Superstaq and Qiskit. And you can probably guess that we're going to see some pretty awesome results. So just pulling down those results, comparing to the ideal probability distribution. And if you pause right after this, right now, here's the final result. So with Superstaq, with this technology that produces these pulse gate circuits, again, there's nothing out there that produces pulse gate circuits that are optimized, we have a 43% 15-qubit GHZ state. That's pretty good. With Qiskit runtime, even at its highest optimization level, we're able to get 2.7% fidelity. So this is a 15x advantage. And the cool thing is that this advantage scales dramatically with the size of qubit array that you're dealing with. If it's a 50-qubit array, we see 100x advantages. If it's a 1,000-qubit array, if it's a 100-qubit array, we see 1,000x advantages. And this is what one of our customers at Argonne National Lab recently used to set a record for building a quantum chemistry simulation of the water molecule. They were able to get a 10x advantage over the best other tools out there, and we're pretty excited about it. And then the last thing here is just, if you're curious, you can see the histogram of visualization of Superstaq results. Again, and if you click play, that'll just finish out the GIF. So everything that I've shown is entirely accessible through our cloud interface and our open source GitHub front ends. And I'd encourage any of you to check it out immediately after this or come to our booth and try it out as well. So this gives you a flavor of what we've been building. And now that I made sure not to bury the lead, I'll go ahead and tell you a little bit more about what we've been building here. So if this works, there we go. If I really had to zoom out and explain our core philosophy behind Superstaq, it is that compilation of quantum programs needs to be aware of the underlying hardware. And we've developed a number of techniques and IP over the last 3 years, and in fact, before that, 10 years of academic work, that bring to the application level characteristics of the underlying device physics to get breakthrough improvements in performance. Just a couple of months ago, we put out a flagship paper with our collaborators at Berkeley, Sandia, U Chicago, Argonne, to explain this technology that underlies our Superstaq quantum platform. And for those technically curious, you're welcome to check out at our archive link. Now, I showed an example from IBM hardware in my demo just before this, but I want to emphasize that this is actually a multi-target framework with universal support for a number of hardware platforms. That includes superconducting platforms for which we've presented optimizations in the paper, trapped ion platforms, and neutral atom platforms as well. And in fact, there are several other hardware targets that are not even explained in the paper, but are available in our software product. What I want to do now is share 2 vignettes of how our existing customers are using Superstaq to achieve greater performance. So the first is QScout. This is our user at Sandia National Lab. It's a really impressive trapped ion quantum computer with very amazing levels of low-level control. And what I thought I'd do is kind of illustrate the layers of what Superstaq can do for them and does for them. Now, the baseline layer is that they can take quantum programs with a standard compiler and rewrite it in the instruction set that their hardware understands. This is called an MS, or Molmer-Sorensen gate. The first thing that Superstaq does is we take their quantum programs that they want to run and resynthesize them to a physicist-friendly gate, which is continuous. Instead of having to do a full turn, you can do a partial turn. We call this a parameterized gate. The second thing that we do is we've designed this technique called swap mirroring, and I encourage you to read more about it in our paper, but the gist of this technique is that, perhaps somewhat surprisingly, you can insert additional swaps into a quantum program to improve its performance. And one of the other layers that we've recently developed is called gate ranking. And this aligns with the fact that there's a lot of heterogeneity in quantum hardware, and it's often possible to steer more of your traffic to your best gates. So this is just one breakdown of the sequence of optimizations that we apply on our customer hardware. And let's look at how it applies to quantum volume. Quantum volume is perhaps the gold standard of benchmarking quantum performance. So what we did is we had the QScout quantum computer run a quantum volume circuit that attempted to achieve its maximal possible quantum volume of 16. And the way to read this plot on the left-hand side is at the very end, we hope that the green envelope is entirely above that pink dashed line. But unfortunately, in the 200 circuit executions we ran with their standard compiler, it does not achieve a quantum volume of 16. It does not maximize the abilities of the underlying hardware. So the first thing we did was threw Superstaq Lite at it, and that's in purple here. What we do is compile to this entangling basis, and if you look, and I'll zoom in now just on purple, just at 199 circuits, we attain this result that the purple envelope is above the pink dashed line, which is to say that we are able to achieve a quantum volume of 16. Now, when we throw Superstaqs with its full power and all bells and whistles, which is just available out of the box now, we actually get that crossover point, the orange, crossing much earlier, 131 circuits. So just to summarize what you've seen here with all three colors together, without Superstaq, this machine does not achieve a quantum volume of 16 with the standard compilation tools, which are already optimized. With Superstaq, we're able to achieve the highest possible quantum volume it can achieve for a 4-qubit device, and it's able to get there a lot faster at 131 circuits. That's something that you can run in just a few minutes of time. I'll now share a second vignette from our customer at the Berkeley testbed. This is the AQT Advanced Quantum Testbed. They have a very impressive hardware platform that, among other things, has support for Q-trits. So Q-trit is like a qubit, but instead of 0 and 1, it can do superposition of 0, 1, and 2. And this is really interesting, let's say, for financial applications, because instead of just having a buy or a sell decision, you could model very efficiently and naturally buy, hold, and sell. And it's also very useful for quantum error correction techniques. But anyhow, what our platform can do for them is produce a pulse sequence that generates a swap between two Q-trits. And the first thing that you're seeing here is kind of the vanilla first thing that we tried. What you see is a pulse sequence led left to right, taking about 5 microseconds. And each of those humps corresponds to an interaction between two of their Q-trits. That was with our optimizations turned off. With our optimizations turned on, there's two things that happen. The first is that the entire pulse train is happening about 30 to 40% faster. And that's really important because especially for Q-trits, the lifetime of these states is very low. The second piece is that each of those humps are now better aligned with the native gate set of the hardware. And what that means is that we are able to perform this swap between two Q-trits with far lower error and far faster. And this is that result. So with this technology, which we call bring your own gate set, we get more than 10x reductions in error. This is essentially a truth table of swapping of Q-trits. If you look, for instance, in the penultimate row, you see that the 2-1 label, that is having a 2 in this Q-trit and a 1 in this Q-trit, with 83% likelihood is going to end up in the column that corresponds to a 1 in this Q-trit and a 2 in this Q-trit. And to the best of our knowledge, this is the first ever experiment that demonstrates swaps between two Q-trits. So this is not just about enabling better performance, it's about enabling entirely new types of algorithms and implementations that were not previously achievable. So I want to emphasize that everything that I've showed is not a hypothetical. You can actually get started with it today. And I certainly welcome the audience here or future YouTubers and TikTokers to go on superstaq.infleqtion.com and check it out. It's like a 2-button sign up. And we've got open source front ends for both Qiskit and Cirq in GitHub. And we've spent a lot of effort in documentation. Everything that our customers are doing is available with nice graphics that our team has put together. So I welcome any of you to try it out for yourself. Every trial comes with a free amount of credits. It's quite generous. We can work with you all to explore other applications as well. So thank you for your time. That brings me to the close of the Superstaq portion, but I also want to plug in a word for the rest of Infleqtion's activities at Q2B this year. And in particular, today's a really exciting day because we launched a really amazing breakthrough platform called Octant for creating quantum matter. And so if you're curious about that, please do attend the keynote session from Paul Lipman, our Chief Commercial Officer, tomorrow. We also have on Thursday a really exciting talk on quantum RF sensing from William Clark in collaboration with our friends at L3 Harris. And if you're not sick of hearing from me, please feel free on Thursday afternoon to come to a joint presentation with our collaborators at JPMorgan Chase, Ruslan, and we'll be sharing details about a really exciting quantum algorithm we developed called QCHOP that solves constrained optimization problems on financial data sets such as ETF arbitrage very efficiently. And the last thing I'll mention is that we've got a booth right front and center with a bunch of TV screens and our full Infleqtion team there, and we welcome conversations with any of you to check out what we're doing live and put it to the test. So with that, I'll bring my talk to a close and really appreciate your attention and hopefully have piqued some of your interest in Superstaq. Thank you. Sure, any questions? Yes.
So you said you have like Qiskit, Infleqtion, or Qiskit Superstaq. Would I have to sign up for an account to use that, or can I just use that as is?
Good question. So baseline, you can go ahead and pip install Cirq Superstaq, Qiskit Superstaq immediately. That has access to a lot of great features out of the box, including our benchmark suite, Supermark. It includes the custom gates that are necessary to present the optimized compilation. To actually get mileage out of this, you do need an API key to use our optimizing compiler, because again, that runs in our cloud. And so that's why to get the full power of this, it's a 2-button click to sign up either with the email or Google login to get that API key.